Bonjour à tous, merci d'être là. Alors je sais qu'il y a les RNL en ce moment, donc ça explique peut-être un peu pourquoi on n'a pas encore plus de monde, mais merci d'être venu. Je vais faire l'introduction en français parce que Rodney est franco-américain. Il parle parfaitement français, mais je pense que tu feras ta présentation en anglais.
Oui,
en anglais, ouais.
Mais pour poser des questions en français.
Voilà, Rodney est d'habitude basé aux États-Unis, mais là il est pendant 1 an en France au laboratoire d'ailleurs. Tu es où?
EM2C.
Voilà, EM2C. Avec une bourse Fulbright. Alors, Rodney m'a expliqué d'où venaient les bourses Fulbright. Et moi, je savais que Bill Clinton avait eu une bourse Fulbright, et aussi Karl Popper. Karl Popper a eu une bourse Fulbright pour aller en Nouvelle-Zélande. Et donc, voilà, Rodney est un récipient, comment dire, a reçu la bourse Fulbright. 2 fois, il m'a dit d'ailleurs, Rodney.
Oui,
Première fois pour ta thèse, et cette fois pour visite en France. Et donc voilà, Rodney est un spécialiste des modèles multiphase, et donc il va nous en parler aujourd'hui.
Ok, thank you. Yes, so je pourrais parler en français, mais bon, je vais faire en anglais. Okay, it's very good to see Daniel Willier ici, because a lot of this work was inspired by the problem of well-posed two-fluid models, and in my opinion, if you have the right physics in the model should be well-posed by itself, and so usually they're treated as a mathematical problem, and so I think that Daniel's papers that I read very closely, especially the 2013 review of this. So it's a very old paper, but so the way this really got started, I was a visiting professor in Ghent in Belgium for a Franke professorship. That was 6 years ago. And I wanted to figure out, using kinetic theory, if you have a two-fluid model based on particles of different sizes, so you can do kinetic theory for collisions of particles of different sizes, the classical Boltzmann-Enskott kinetic theory. The kinetic theory is well posed because you have a kinetic equation, and the eigenvalues are all positive, etc. So if you use that limit and you took the limit of where you had big particles and very small ones like a gas, what would you get? And so you end up getting additional flux terms, a term in the flux that makes the system hyperbolic. So deriving it from kinetic theory. It wasn't quite enough. That worked well for gases, where the ratio of the particles were large compared to the ratio of the gas. And of course, if you look at well-posedness of kinetic theory, it's the buoyancy term that matters. And so what we want to do is then go to emulsions or bubbles. And in that case, you need some extra terms. So what I'm going to talk about today is how to do kinetic-based multi-scale models. And also, I'm going to look at, I have a project where we're looking at bubble size, or particle size distributions or bubble size distributions, and so how to do the two in the same framework. Okay, so that's kind of the background. First, let me just give you some examples of multiphase flows that we're interested in simulating. So typically, one of the big examples that we've been working on recently for biomanufacturing, where you're injecting bubbles into a liquid with a broth for fermentation. So here you can see a case where you're injecting monodisperse bubbles. It's fairly dense, about 30%, or more like in an industrial application, you have an asparger at the bottom and you're injecting, so you get polydisperse bubbles where you have a large bubble due to coalescence and you get recirculation of bubbles. So we want to be able to model that for the whole apparatus. Okay? We could, I guess, use Basilic, but we couldn't do the whole apparatus with Basilic. So, okay, so that's one typical example. So you have very light drop bubbles in a heavy fluid. Another one that we're interested in is sedimentation. So this is, I think I stole this from Olivier Desjardins. He did a simulation. So this is following particles in a Lagrangian framework, but coupled to a fluid. So you have a turbulent flow in a pipe, and it's transporting particles in a pipeline. So slurry flows and sedimentations, where the particles are heavier than the liquid, but not a lot heavier. Maybe a factor of 2 or 1 to 2. Another one that's, I put this in for where I'm working at now at EM2C. They're interested in spray combustion. So you have a spray that comes out here, and so we like to model the spray and its combustion. So not necessarily the drop breakup part of it, but the part after it when it becomes a dispersed phase. And then one that's very common in chemical industry is fluidized beds. In a fluidized bed, you inject gas at the bottom. You have a packed bed, and if you inject it fast enough, high enough flow rate, then it becomes fluidized. It acts like a fluid, and then you also get bubbles. So this would be a very dense setting where you have very dense particle-particle interactions that as you increase the gas flow rate, it becomes a riser. And in a riser, the particles are being moved upward. And so you can see you form these structures. We call them clusters. And so our two-fluid model should be able to resolve these clusters. It should be able to resolve bubbles. Okay. We're not going to do it at the size of the individual particles, which are on the order of 90 microns. But we should be able to capture the large structures. Finally, one that I've been working on a lot recently, I have a project with the Department of Defense in the US. They're interested in explosions, how particles are projected in explosions. And so this is an experiment that's done at Sandia National Lab in the US, where they put in particles, either, and this most of the experiments are monodispersed, but they also have some bidispersed cases. So these particles they're put in at a constant, make a sheet, a curtain that comes down. They can control the volume fraction in the curtain, usually it's about 20%. And they control the size of the particles on the order of 100 to 200 microns. And what you do then is you put this in a shock tube. And a shock tube, you release a shock on one side, and then it comes through and it goes through the particle curtain. And you're interested in the spreading. How does it spread due to the drag and the collisions? It's dense enough that you get particle-particle collisions in here, so there's a pressure and there's also a drag. And so here, as you can see, these are the plots where you have position. So this is the curtain location, and this is time. These are very short simulations, typically on 1 millisecond is enough to capture a shock. And what you're looking at here is the gas density, so the shock hits and reflects back off. And then here you've got the particle curtain for the volume fraction. You can see initially it compacts because the shock hits and compacts it, and then it spreads out. And what they're interested in is particle size distribution. So they have, when things break up in real systems, they have a fairly large particle size distribution. And so here's D32, the volume over the surface area. You can see that when you look at it, you get particles that are very small, that get taken away very quickly. And then the average particle size is here, so the big ones get left behind. So we want to be able to think that. That's the small ones. So I'll show you later a trace, but this is a mixture of particles, and the smaller ones have all been taken away, so they're around 10 microns. And the ones that get left here are about 300 microns, and so they get accelerated faster. So you can see at the beginning they're all the same. Also interesting here, you can see you get bounce back of big particles. That's due to the collision and pushing back. So they want to be able to predict this. The application is they're actually going to combust the particles afterwards, and they want to know whether the small particles are mixed with the big particles during the combustion. Okay, so the modeling objectives that we're trying to achieve for the two-fluid modeling, well, we want to have a WellPosed model. I'm not sure whether that's a concept that everyone understands. I know Danielle does. A WellPosed model is that the eigenvalues of the system of equations, like, for example, Euler's equations, is WellPosed. When you add more equations for each phase, the eigenvalues have to be real and distinct. Why does it make a difference? Well, if it's not WellPosed, then you put it in a code to solve it, it's going to just oscillate and blow up. So any physical problem should be WellPosed, in the fact that all the eigenvalues could be positive. The reason why it becomes a problem, though, is because when you add a second phase, the buoyancy term typically causes the problem to have complex eigenvalues if you don't have the right physics. So that's what we have to get around. And we want to do polydispersed particles, because we want to do the segregation problem. And we want to be able to do both high and low speed flow. So the shock is a high speed flow, 200 meters per second or higher, and low speed flows would be like a settling problem, which is gravity driven. We should be able to do both. We also want to do particle phases where we have very dilute cases, very dilute, maybe 1%, typically in most applications, and then very dense, like the case I showed you for the fluidized bed, where the particles are touching each other. So from both a kinetic regime to a frictional regime. We have particle size distributions that are typically very broad. For example, log normal for the particle curtain that they use. We also want to be able to capture pseudoturbulence. Pseudoturbulence is important for transfer of momentum and energy in the fluid phase. I put a picture here of a direct numerical simulation from Jesse Capizolatro's group. So this is a shock going through a particle curtain. And the shock here has already gone through, so you see the subshocks here. But what you want you to focus on is the vorticity in the fluid phase, so in the gas phase that's behind it. So because the particles are finite size, they have wakes, and the wakes create a lot of turbulence. We call it pseudo-turbulence because it's not shear-driven turbulence. It's turbulence, it's combining turbulent wakes and shocks in front of the particles, and you can see it gets transported downstream. And so that's typical pseudo-turbulence. The same thing happens for bubbles. You get the wakes behind bubbles or any finite-sized particle. So we're going to have to include that because that's going to change, for example, heat transfer rates and momentum exchange terms inside the fluid. The other thing we're going to include is added mass. So if we want to do bubbles where the bubbles have basically no mass, if you 1,000 to 1, so the ratio. In order to do a two-fluid model, you have to include an added mass term. And I did this in the way that Cook and Harlow did it in 1984, and typically the way it's done in bubbly flow. I simply said, well, instead of trying to do an added mass as a force, I'm going to do added mass as a mass. What that means is that I take my particle, say, assume this is a particle, it's very light, and then I have some added mass, the wake behind it. And I'm going to split my two-fluid model. Instead of having the two phases, I'm going to have the particle phase plus the added mass, which is the star, will be convected with the velocity UP. And then the rest of the fluid around it will have its own velocity UF. Okay, so what that means in practice is that the average fluid velocity in the whole fluid will be the sum of UF times its weight, alpha G star, and then the fluid here. So there's a difference. And in the paper of Cook and Harlow, they show that it gives you exactly the same thing as a virtual mass force. You do the change of variables. So this is convenient in a kinetic theory simulation because you can treat this as your particle with a different mass. Okay, so if we look at the physics of these polydisperse multiphase flows, what do we need to get right? Well, it depends on the ratio. And I give a z here for the ratio between the fluid density, so the material density of the fluid. So, for example, for water, it'll be 1,000. For air, it'll be on order 1. And then the density of the particle, the solid particle. So if it's a bubble, it'll be 1. If it's a solid particle, it can go up to 10,000, for example. So the z ratios are important because it's going to control the time scales. Right? So some examples I put here just to show you what physics is most important for each of the different values. So z much bigger than 1. That corresponds typically to bubbly flow because you've got 1,000 here and something very small, so over 1,000. In that case, you need to have added mass to get the time scales correct for acceleration. You have buoyancy, of course, due to gravity. You have a drag force. Slip pressure, I'll explain what that is later, but that's what makes the system hyperbolic if you have this, what we call slip pressure. And if you have flows with gradients, you need also the lift force. If you go here where you're slightly much less than 1, so these will be droplets, for example. You have drag, of course, is the main one. In droplets, you also need to include evaporation. You also have the slip pressure term, which makes it hyperbolic. And then you get gas pressure gradients that act like buoyancy. Solid particles and liquids, for example, the sedimentation problem, where the particles are moving relatively slow compared to liquid phase. So order, it's less than 1, but not a lot. You have drag force. Slip pressure turns out to be very important in this case. Added mass is important, but not as important there, but it's still important to get the right time scales. And buoyancy and lift force. And then finally, if you do the riser problem, where you have particles being taken up in a riser, so heavy particles in the gas, so drag force, then the main things you need to get right are fluid drag and then collisions, frictional pressure. Because the particles have a lot of random motion, there's a lot of collisions involved. Okay, so those are the physics, and then we want to just have one model. We don't want to change the model every time. We want one model that includes all the physics, and then you can use it in any range. Okay, just some notation. So when you do these problems, in all my cases, I'm going to have a two-fluid model that includes a mass, momentum, and energy balance. So I'm going to keep track of energy. It's really convenient to do this when you do compressible flows because energy is conserved, and so you have to make sure everything balances. So just some notation for this. So we have mean kinetic energy, which is the velocity squared, the mean velocity of the particle phase squared, and the gas mean kinetic energy. We then have pseudoturbulence. We want to keep track of things on the scale of the particles. So we have a pseudoturbulence part of it. In a particle phase, we call this granular temperature, theta p, but it's the same thing as particles having random motion relative to the mean flow. And in the gas phase, I showed you the picture earlier, kg is the magnitude of the fluctuations in the gas phase. What happens then at the heat transfer level, we have the temperature of the particles. Well, if you have collisions and they're inelastic, they can heat up, or they can heat up due to heat transfer. But at the end of the day, all the energy in the flow will start over here and end up over here, heating up the gas. Okay, so if you just looked at the equations here, would be Euler's equations, right? And then up here is a similar thing. It looks like Euler's equations for the particle phase. So some notation: the total energy for the gas phase is the mean kinetic energy, the pseudoturbulent kinetic, and the internal energy of the gas phase, and the same thing for the particle phase. And I've written these so they're at the same scale. So these things are on the particle scale, and these things are smaller than the particle scale. So that's the multi-scale part of it. We keep track of it. Okay, so the modeling approach that we use, there's two modeling approaches you can do. You could write down the continuum equations and do volume averaging. That's the classical way of doing it. That would get you from what I call the microscale model, the direct numerical simulation model, down to a macroscale or Eulerian model. What we're going to do, though, is what we call a kinetic theory model. So we're going to postulate a mesoscale, so how particles interact with each other. Here, you don't have any of that. Well, you'll average, and then you've got to figure out the closures. Here, we're going to implement what we call mesoscale physics. For example, Boltzmann's equation as part of particle collisions for hard spheres, or how things interact. So we put a constraint on it. So this is going to work well for dispersed flows because we can follow individual particles in the dispersed flow. So we're going to have a microscale to a mesoscale. So we're going to have a kinetic equation. The kinetic equation is just a high-dimensional equation that keeps track of the distribution of particle velocities, the distribution of particle temperatures, compositions, etc. And we have to write that out and close it using the macroscale information. So, for example, if you do direct numerical simulations, the terms that appear in this equation will be closures that you derive from the direct numerical simulation. These are typically solved currently using Euler-Lagrange methods. So if you're familiar with Euler-Lagrange methods, you take a fluid and then you follow all the individual particles in the simulation. That's the one I showed you for sedimentation earlier. So you have like 1 billion particles, you follow each of them, and so it's fairly costly, but you use a drag model, whereas here you wouldn't use a drag model, for example, or a heat transfer model. Okay, that still doesn't get you to where you want to go. We want to go to Euler-Euler models, so we're going to take the moments of this kinetic equation, and then there'll be a closure that will be required here, because the moments of higher order, just like in Boltzmann's equation, you have to know something about interaction timescales. But the advantage of this is if you can do the mesoscale model, then you have some physics built in, and this equation should be hyperbolic. And then when you do this, it's just equation, is your closure is hyperbolic that you get from the other system. Okay, so that's the idea. So let's just review what microscale modeling is. So direct numerical simulation, I took this from a colleague. So direct numerical simulation, well, it's exactly what it sounds like. You solve for individual particles with Newton's equations for linear momentum and angular momentum. And if you do heat transfer, mass transfer, you can do that on the particles. So you have a grid that's much smaller than the particles. So typically, for example, this is a bidisperse case. And so the particle diameter here, you have at least 30 grid points across the particle diameter to resolve it. It's even harder for bubbles because you have to resolve the interface. But the idea is that you're going to resolve all the relevant physics. And then we're going to look at the difference in velocity. So in the kinetic model, we don't know where the particles are. All we know is their distribution of velocity. And you can see here, for example, the particle velocities, the big particles, they're much more massive, so they have lower velocity. But we still have a distribution. And then the smaller particles, we have some that are moving very quickly, and some that are moving very slowly. So our kinetic model, we're going to try to capture the particle velocity distribution, but we won't know where they're at. Here's another example for if you want to do high-speed flows, gas particle flows. Same thing, except now you're going to be solving Euler's equations for the gas phase. You have to resolve the shocks in the flow. So there's a shock. So this is different Mach numbers. This is Mach number 0.1. And you can see there, this is the pressure field in the Mach 1, and this is the pressure field in the Mach 1.2. And so what you see here is that, as you expect, at low Mach numbers, the pressure is nearly uniform, but at high Mach numbers, you get the shocks in front. So we want to, so if you write, for example, a drag law, the drag law is going to depend on the Reynolds number of the particles and the Mach number, because the Mach number is going to change the drag. Here are the velocity fields for the cases there. You can't, they're not that much different, but you can see that there is a difference in the drag coefficients. So microscale simulations allow us to get drag coefficients for Mach number, heat transfer coefficients for Mach number, and also we can extract things like turbulent kinetic energy that we have to model that's generated due to drag. Here's another one that I also find quite interesting for two-fluid modeling at least. This is a sedimentation problem, and it's the group at Delft, Wimpen van Bruggen, and you can see they've done DNS. This is a paper they've submitted to International Journal of Multiphase Flows. They gave it to us some time ago, so we've been working on it. So this is particles monodisperse falling due to gravity. So they're solving a Navier-Stokes equation for the liquid and Newton equation for the particles. They calculated drag coefficients. It turns out Richardson-Zaki works very well for this case. They computed pseudoturbulent kinetic energy. They computed the granular energy of the particles. So the particles have their own, they don't all just fall uniformly. They create structures that fall faster. And interestingly, they computed something called kinematic waves. I don't know if you're familiar with that. Well, these are waves. So this is a space-time plot. So they took averages over every slice, and then they plot them versus time in the y direction. So this is the vertical direction, and this is time. And what you see is that there's the black line is just the particles falling speed. So that you get from the drag law. So the particles, there's a structures that go like this, and you can see them, and you look at it close. That's just the particles moving downward at the settling velocity. But the kinematic wave is the part that goes up. So there's a wave that moves up through the particles. So it's not the particle speed, it's a wave that's generated by the fact that there are particle-particle interactions through the fluid. Okay. It's not due to collisions, because there are very few collisions in these cases, but the fact that they have different pressure fields and as structures develop. What they did is to take a seventh order Fourier transform of this, and you can then pull out the wavelengths, okay, from their data. So they have these plots, and then you can clearly see that these kinematic waves are there. So one of the things that two-fluid model has to do is predict the right kinematic wave for these problems. Okay. Okay, and then this is what I've been working on with Basilic. This is a case of a breakup of turbulent drops. So we're interested in a problem with BASF, which is a chemical company in Germany you might be familiar with. They're looking at turbulent breakup of emulsions, and so they have droplets. You put the droplet in the turbulence. You can control everything, of course, in a microsimulation. And then we're interested in what happens to the droplet when it breaks up. So in terms of the Weber number, so you can see that eventually the droplet breaks up into multiple strings, but it makes a very long string with a capillary effect. And that's caused by the fact that the viscosity in the drop, we set it to be very large. So if it were a bubble, it would simply break mainly two or small. But when you put the viscosity, then there's a resistance to breakage, and you get these fact with very large distributions. So you can get child size distributions, breakup time scales, all depending on the Weber number. So we can then use that in the mesoscale model. Okay, another example of microscale is this is bubbly flow in a channel. This is work that's been done in the CUA in Saclay by the group of de Clouseau. And so here they're looking at bubbles rising in a turbulent channel flow. And again, these are classical type simulations. So what we're interested in is how is the pseudo-turbulent kinetic energy affected by the bubbles? generation, what are the forces, etc. So all of this information you get from these simulations you can use in the mesoscale, model. Okay, so just to cover that, so basically there's lots of advantages of microscale modeling because you have access to all of the data, all of the physics. The problem is the limitations, there are just too many details for the next level, so you have to ask the right questions in order to get there. We can't use these for the industrial geometries that we're interested in and for large-scale systems. And so the limitation is, of course, we want to do a bigger system. The cost is too high to get the same accuracy. Okay, so we want to use a mesoscale model, and so we can reduce the computational cost by taking out all the details of the individual particles and replace it with either a sample of particles or which would be an Euler-Lagrange type simulation or a kinetic model. So the difference between the two, this Euler-Lagrange, I'm thinking of cases where you have direct discrete element methods where you follow individual particles, and so you're solving Navier-Stokes equation for the continuous phase, Newton's equations. Unlike in the microscale where you resolve the drag, here we're going to use the drag coefficient. So we have correlations for drag, lift, and added mass. And the reason that this is faster is because you can use a grid on the order of one particle diameter, for example. So typical examples that I'll show later, the particle grid size is 1 diameter typically. Okay. So it's still expensive because you're solving, say, 10 to the 7th particles, and the grid is still fine, but it's less costly than the microscale. To make it even more affordable, we're going to use the kinetic model. In the kinetic model, you don't follow the individual particles, but we solve a kinetic equation for the particle phase. So just like Boltzmann's equation for gases, we're going to do the same thing for the discrete particles. And then we have to model, in this case, we actually resolve particle-particle collisions. Here we'll have to model them. For example, using the collision model. We'll use the same thing for correlations that we use in both cases. And here you get larger time steps because, for example, in the collisional flow, you have to use if you do a direct simulation of a collisional, you have to use a very small time step to capture collisions. Here we use the model for collisions, so we can use a larger time step. The grid size is about the same. It's still about 1 particle diameter, but we have a larger time step. It'll be controlled by the kinetics by the time scales of the two-fluid model. Okay, here's an example of work that I did with Jesse Capsulatro some time ago. So we were looking at Euler-Lagrange models for gas-solid flow. So this is a riser that's periodic. We have particle densities much higher than the gas, and all the different physics, the soft sphere collisions. And what you see in the Lagrange model, you capture the structures. So you couldn't capture these structures in a microscale simulation because you can't get a big enough box. The key here is that the box size has to be at least 100 times bigger than the particle diameter, preferably 1,000. So in order to capture the clustering that happens naturally inside the riser, once you have the Euler-Lagrange simulations, you can take out, for example, the granular temperature, the theta p, and you can also compute the volume fraction. A two-fluid model should be able to produce the same thing when we get the kinetic model. Here's another, this is kind of the same thing, just to show you how the physics works. So we start out with these simulations with the particles uniformly distributed, and the physics here is that once they, due to interaction through the fluid, they form clusters, and then these large clusters fall through. So almost all of these multi-phase flow problems have clustering in them, whether it's the bubbles going up or particles coming down. You get clustering through the interaction through the fluid. Here's the sedimentation problem. Here's a Microscale simulation we did with the same code. So we tried to simulate the one I showed you earlier with the kinematic waves. And so this is an Euler-Lagrange simulation. This is a snapshot of what the particle velocities look like. So you can see, even though the particles look, they should just fall down directly. In fact, they don't. They form 3D structures where you get fast-moving groups of particles and slow-moving. And so there's clusters forming in that case. The density ratio here is only 1.5, so it's not a huge density ratio, but you still get clusters. This just shows you that as a function of volume fraction from 0.01 to about 30%, you get very good 30% to 0.2%, you get good agreement with Richardson-Zaki law for the mean settling velocity. So we get a coefficient that looks like this for the average. What's the average velocity of settling? And what we've added here, and the important I'm going to talk about in the two-fluid modeling, is something called slip pressure. Okay, so slip pressure has to do, so we want to, there's collisions are not strong enough here to affect the kinematic waves. Okay, so we have to have some other mechanism, and the mechanism we're going to use coming from kinetic theory is what we call slip pressure. And so you have the difference between the mean fluid velocity and the mean particle velocity at any point. You can use that to form a second order tensor. I call it a pressure, but you could also turn it into a stress by making it minus. Dwayne Zhang has done that at Los Alamos. And you get two parts. You get the isotropic part of this tensor and an anisotropic part that has to do in the direction of the slip. I call it slip pressure tensor. You could call it fluid particle fluid tensor, depending on what you want to call it. But the important point is it depends on the mean velocity difference. It doesn't depend on granular temperature. So even if the particles had no granular temperature, you would still have a pressure that keeps the particles apart. The only constraint on it is it has to be positive definite. Otherwise, this code would be unstable. So it's a positive definite tensor. And notice that it doesn't depend on the particle density, but on the fluid density. So it's a force, it's a pressure through the fluid between two particles. So it depends on the fluid density and the particle volume fraction. Okay. If you look at, for example, granular pressure, it's multiplied by the granular temperature times the fluid times the particle density. Okay. In order to implement this in a two-fluid model, we take the divergence of this stress of this pressure tensor, and it becomes a force. So we add this additional force in the two-fluid model. And the reason why we had to do this is because if we neglect this force, we're not able to predict the fluctuations correctly. And so adding this force gives you these results. So these are RMS fluctuations of the particles at different volume fractions. Okay. So we have the DNS data from the group from Delft, and we know exactly what they should give us as a function of volume fraction for the system. Those are the symbols. And then we did first simulations with no particle fluid particle pressure. And what you see is we're up here and we're here, so the fluctuations are too large. So the particles are not seeing each other through the fluid, so they can vibrate, they can move around more randomly, and they're too anisotropic. We expect them to be anisotropic because the gravity is in the vertical direction, so that you get more fluctuations there than you get in the horizontal direction. So that were expected, but you see here they're off by a very large amount. So the anisotropy is too high. If you put in the PFP model, we use the coefficients that were found from a paper with Balachandra in 2021. We used their coefficients, and you can see we were then able to reproduce with just one additional term, the PFP term. We were able to reproduce the velocity fluctuation, both the magnitude and the anisotropy. So that was the first for us, an indication that you need that force. You need that force there. More importantly, though, is what happens to the kinematic waves. It turns out the speed of the kinematic waves, the slope, is just determined by the drag law. So Richardson-Zaki tells you exactly what the slope is going to be. You take the gradient and you can see that. But the wavelength, though, depends on the pressure. So if you add this PFP term, if you don't add it, you get very short wavelength structures. You get if you see this in a falling wave in 1D that I'll show you later, they're just going to be waves that are going down. And the wavelength here was too short relative to the DNS. But adding the slip pressure, the slip force, you get wavelengths that are longer, which makes sense because they're resistant to fluctuations. And we're able then to reproduce the DNS value. So that's the interesting thing about this is that we can now say, okay, if we need data for fitting the coefficients, which is very hard to get from DNS the way they did it in Balachandra's group, if we look at kinematic waves, we can actually parameterize using kinematic waves in the DNS, which we can extract the way they did in Delft. Okay, so kinetic model. Let me just go over this very quickly. So we're going to do kinetic theory model then, is we're going to use the kinetic equation. So we're going to say the number of particles at time t at location x with velocity u. So we have a distribution of velocities and some property c. C, for example, is the size distribution. Okay, So remember, an NDF is like in Boltzmann's equation. It's the average number of particles per unit volume at time t with some properties. Okay? That's what we're looking at. From the Euler-Lagrange simulation, we can actually write down this equation that's consistent with the Euler-Lagrange simulation. You get some genetic terms. You get the accumulation term. You get the transport term due to the particle's velocity. So this is a variable that's distributed. We get a force term. This is rate of change of velocity due to drag, or the PFP term, for example. And then we get rate of change due to, say, size due to aggregation or breakage. That would be the G term. On the right-hand side, we have processes that happen instantaneously, such as collisions or aggregation or breakage, and we would have models for those cases. Okay, so the idea then is to take this equation that's then coupled to Navier-Stokes equation. Where will Navier-Stokes come in here? Well, for example, for drag, the A term, we need to know the difference between the mean velocity, the particle velocity, and the fluid velocity. So there'll be a coupling there. Anything that change forces or exchange energy. So I'm not going to take an average of the instantaneous equations in the two phases and try to figure it out. Instead, I'm going to write a kinetic equation and then use what I know from Euler-Lagrange to parameterize it. Okay, the coupling though is done through the moments. So let's do a monodispersed gas solid flow, and for the particular example. So here I've written down the equation. I've normalized the function f such that when I take the integral over the velocity, the only thing here goes on is velocity. And so I normalize f such that when I integrate out velocity, it's the mass, and the mass is rho p times alpha p. Just the mass of the particles in my per unit volume. This is basically a kinetic theory. This is Boltzmann's equation, but it's in Scott-Boltzmann because I'm using finite-sized particles. And so I get the transport of the particles due to the velocity. I get the pressure. This is an approximation for kinetic pressure. So this is collisional pressure. Particles colliding with each other creates a pressure, or frictional. If they're actually touching the dense regime, they push back from each other. So we have those two pressures. Okay, that's going to appear over here as a flux. And then in terms of forces in the equation, we have acceleration due to fluid drag, which is tau p, calculated with a correlation. We have the buoyancy term here. We have the PFP term here. So this is exactly how we added in the Euler-Lagrange model. So we put it into the Euler-Euler model as the divergence of the pressure. Okay, so if you're familiar with, this is a collision source term. So just like in Boltzmann's equation, you have collisions, and collisions conserve, they conserve mass, collisions conserve momentum, and then they can change energy for inelastic collisions. And likewise for frictional, you conserve mass, momentum, and you dissipate energy. So this is our starting point. So if I were doing microscale simulations, I would want to go and check each of these models. And once I had those models, I can go on from there and get a two-fluid model. So the idea is this is based on what you learned from microscale, and then once you have this, you can go now to macroscale by taking moments. Okay, so what are the moments that we're going to use? We're going to stop at total energy, so we're going to take 3 moments. And so what we're going to use is mass. So we're going to just take the integral of f to get the mass. So it's the volume fraction of particles is alpha p, and rho p is the density. Multiply by u, just like you do in Boltzmann's equation, you're going to get the momentum of the particle phase. We'll have mass, momentum, and energy also for the gas phase, but we know how to get those from Navier-Stokes. These will give us the coupling terms. And then the total energy, kinetic energy, is just u squared times f. So procedurally, what you do is you multiply this equation by those 3 terms, and you integrate. And then you see what comes out. Okay. We then have to approximate that. So we use the finite. We're going to have actually 7 equations in our 2-fluid model when we're done. We're going to have mass, momentum, energy, and we're also going to solve for the volume fraction. And I'll tell you later why we need to do that. So we're going to have 7 equations. So it's like 2 systems of Euler's equations coupled together. And so we're going to solve the kinetic equation of Navier-Stokes. And we'll know what the density of the gas is. It's compressible, the velocity of the gas, it's the total energy of the gas, and F, if we solve it directly. You could solve it with direct simulation Monte Carlo, but we want to use moments instead. And when we do moments, we get a macroscale model. And so we're going to have the continuous phase equations. I won't say too much about these, but they're going to be just compressible Navier-Stokes with coupling terms due to energy and momentum. Important thing here is that they're compressible Navier-Stokes, but the energy and momentum fluxes change because of the coupling between the two phases. And then we're going to have the particle phase with moment equations we get from our kinetic equations. So the one thing that I haven't talked very much about, it's not very important for this case, is that, for example, the moments must be realizable. What that means is that when you solve for the energy, it has to be positive. The total energy is positive. Okay? The other thing that has to be is WellPosed. So that means that the system has to have positive eigenvalues for the fluxes. Okay, so if I go through those steps, then I start with the kinetic equation that I showed you earlier. I take the integral of that with F, and I get just the mass balance. It's very classical. There's no mass exchange between phases, so there's nothing on the right-hand side. Do the same thing for U times F. I get an equation that looks like this. So this is just, inertia, accumulation. This is frictional pressure due to the particles hitting each other. And the particle pressure, this is kinetic part of it, and then the particle pressure. This is drag, this is buoyancy, and this is the PFP term that shows up. Theta P here is a closure, so we need theta P is just defined in terms of the total energy minus 1/3 the mean energy. So it's the fluctuating energy of the particle phase. But this is a new term that you wouldn't get if you didn't include the PFP term. For the energy, you get an equation that looks like this. So this is the total kinetic energy of the individual particles. So it's Kp. You could subtract out the mean to get theta p, but it's easiest for a compressible flow to leave it here. So you get theta p times up. That's compression work. You get up times the collisional and frictional pressure. That's again compression work. This is buoyancy term. This is the drag. I didn't write it out, but you can see it's closed once you have a drag model. We have the PFP term, so this does work. And then we have heat exchange between production due to the particle collisions. If EC is equal to 1, you don't generate any energy. But normally with particle systems, you lose energy, and so it heats up the particle phase. One thing I note here is that we're closed. This is a closure. That's why I made it red. Normally, you would get a second order moment. You get a third order moment when you do a Boltzmann equation. But we're going to assume that the collisions are frequent enough that we can approximate, at least for this high-speed flow, we can approximate the distribution function by Maxwellian. So Maxwellian then gives you, for the third order moment, it gives you theta p. Okay, so then the gas phase equations look like this. So we have the PFP term. Notice we modified the flux of the gas phase by PFP. You'll get that's the same term that I found when I did the kinetic theory derivation. It turns out it doesn't make much difference because PG is so much bigger that you don't see very much difference in the fluxes, so it doesn't really change very much. It also appears over here, in any case, as a force term due to the interaction between the particles, so they in fact cancel each other. You can cancel them. So really what this pressure term is doing is adding a pressure into the particle and particle phase. But you can see it's a barotropic pressure in the sense that that when you take the dot, it doesn't change the energy, it changes the, so it's a barotropic-like pressure and then the heat transfer. So these new terms that come from these additional fluxes. Okay, so let me just say one word about what do we mean by WellPosed. So I showed you the equations we have for the two systems. They're equations for the vector x, which has, you can see it has, like in this case, six values. To check for whether it's WellPosed, what you do is you take the flux terms, just the first order terms, and the source terms that depend on derivatives, and you get the Jacobian of that. So you can do that analytically, or you can do it with MATLAB. I did it with MATLAB symbolic. So once you have your equations, for example, this is for this variable here, here's the flux. So we know what it is. There's also the pressure gradient here, which you treat as, which also makes it depends on hyperbolicity and this term. Likewise for EGs, you can see that the flux here is this term, And so what you have to do is line up your variables as a vector, x, and then you write it in terms of the Jacobian matrix of the fluxes. So the Jacobian matrix, so it's nonlinear, so it depends on the local values of variables, right? So for model to be well posed, this Jacobian matrix has to have real and distinct eigenvalues, and for it to be globally well posed, they have to be real and distinct for any value of x that's physically realistic. So if you put in 0 granular temperature, you still have to have real eigenvalues. So you can do this analysis, and we published a paper on it. And you can show that because of this slip tensor, and this is kind of comes from Daniel's paper, this is a kinetic energy term that you've added. It adds pressure. So it's because of that term, and actually added mass plays a role also. As long as that term is there, the system is well posed for any value of x. So that's the important result. And then you can, once you've known that your system is hyperbolic, then finding the solver for it. There's lots of mathematicians that work on hyperbolic flow solvers. We used a flow solver that uses HHL for the gas phase combined with Awesome Plus for the particle phase. Okay, and then we can use the Jacobian matrix to get the eigenvalues, and it's very robust. Nothing funny will happen. If you happen to try to solve this and this had a complex eigenvalue, these things would blow up. They wouldn't work. So that's why you have to have them. Okay, I don't know how much time I have. Do you probably done. Okay, so let me just show a short word on polydisperse. So you can use the same, once you start down this road, then you can use the same thing for polydisperse. So the particle curtains that we're looking at have distributions of masses of particles. What changes? Well, the only thing that changes is everything's the same. You add terms that depend on size. Collisions depend on size. And so you can then write down the same kinetic equation, and then you have to look at the moments. So we use the moments now weighted by the particle mass. And so we need in this case, three moments in terms of particle mass. So the corresponding ones for the mean mass, momentum, and energy are just the first order moments, the average with the mass. And then we could take two more moments, which are the 0 order and the 2nd order. And from that, we can represent the distribution in terms of two other pieces of information. So for example, if you have a log normal distribution, you need the mean, the variance, and the number. So that's what we'll have exactly here. The number of particles, the mean size, and the variance. Okay? And so we can fit that in. We'll also have the same thing for the momentum and for the kinetic energy. So the idea is that once you've got the physics for the monodisperse to work, you can easily add polydispersity to the problem. If you have things like coefficients and breakage, you have some additional terms. I didn't put them in here, but at least the transport part of it will be the same. So what you do then is solve equations, and we use quadrature-based moment methods. So once you know moments, then you can get representative. Basically, the idea is that if you know these three moments, then you can get number of particles of size 1, number of particles of size 2 by quadrature, Gaussian quadrature ideas. And these things change with space and time, and then they equal to the moments that you start with. Okay, and then you end up with equations that look like we had in the monodisperse case, except we have some ratios. And again, this case, because of this PFP term, this turns out also to be hyperbolic, and even though we have, in this case, 9 equations to solve for just the particle phase. Okay, so let me do a couple of applications to show you how these things work. So one of the problems that we were interested in is a creation of a foam. So this is where in this case, we put in very light particles. You can think of them as bubbles that don't coalesce. And we let them rise to the top, and they create a foam on top. Okay. So to do this, I just inverted gravity because I'm also going to do sedimentation. So here in this case, gravity is pointing upward. And so we're going to start with the bubbles here, and then due to buoyancy, they're all going to move down here. Okay, and this is actually a difficult problem because of the density ratio. So we're using 1 millimeter particles. The density ratio, the fluid is water, and the bubbles are 1 meter per second. And what I'm just trying to show here is that because of the collisional pressure term, the frictional pressure term, we can actually create a foam. So we start with bubbles and a foam at the top. They're well packed, close packed at 0.63. And then as gravity pulls them all down, you can see that initially they accelerate very quickly, and the yellow lines, that's because, of course, individual bubbles by themselves rise much faster than the group because of the Richardson-Zaki law. And so they fall very quickly, and then they create a layer at the bottom that fills up. So with hyperbolic flow solver, it's very simple to do this. You just put in a time step, the eigenvalues, and it computes it. It's very robust. This is just to show you what the slip velocity is, the difference between the velocity of the fluid and of the particles. And you can see they're not too high because of the added mass term, but they're on the order of 10 centimeters per second. So initially, they're zero, and then they speed up and they go down, and then you go back to slip velocities of zero at the bottom. So once you have a hyperbolic WellPosed model, you can do problems that are quite complicated in terms of the physics. They go from dilute to very dense in the same model. Here's just to show you what some of the other variables look like in that problem. So, for example, this is the pseudo-turbulent kinetic energy that we're solving for. I didn't show you the equation, but it's an additional equation. And you can see that in this problem, the pseudo-turbulent kinetic energy is on the order of 10 to the minus fourth. But that makes sense because the slip velocity was 0.1. So if you normalize it, it's on the order of the slip velocity squared. This is the granular temperature. Maybe you think that the very light particles wouldn't have granular temperature, but because of the wakes, if you look at bubbles rising, they move around very quickly, even though they have no momentum themselves. So that's a fluid. This part of the model is driving this part, and they're very strongly coupled through the drag term. And this is this PFP term, and you can see, well, it looks almost exactly like the PK term. It has the same magnitude and the same size. But that's again because this is produced. Slip pressure is the velocity difference, and this has a source term, which is the velocity difference for their coupled. Okay, then I did the opposite. So now I'm going to do a sedimentation problem. I put gravity back in the other direction. So just to show you that if I choose a density difference that is the same as with bubbles, you have added mass. So most of the dynamics is controlled by the added mass. So I flip it, and I choose a density that gives me the same time scale as the added mass. And so everything looks just like the inverse. So the model, now we're starting with the particles at the top, and then they're falling down, and they form a layer at the bottom. And so if you flip this over, it looks just like the other one. So in that case, so that's to show you that the density, that we can do any density difference for this case. Likewise for the other parables, the turbulent kinetic energy, the pseudo turbulence, the granular temperature, it's again small, but it's on the same order as the pseudo turbulence, and then the slip pressure, which is making it hyperbolic, it looks like this as it changes with time. Okay, so that was very nice, but then I wanted to say, well, how about kinematic waves? So I wanted to show that the model gives kinematic waves. So I took a density ratio a little larger, and that's only because it falls faster, so the waves are generated more quickly. I had to take a longer domain and make it continuous, and so what we're looking at is a 2-meter high domain. And what I'm showing you is alpha p at different times. This is the volume fraction of particles at different times, and I think you can see there's a wave going up here. That's the kinetic wave that's going up. So you can see all the particles are falling, and then they get very large fluctuations in alpha p. They're like plateaus. So the particles make a plateau, and then the ones in front fall away. So they pile up, and that moves up. So the two-fluid model does predict kinematic waves. In the PFP term, you definitely need it, otherwise it would not be hyperbolic in this case. Here's another example. At 5, you get the kinematic waves. You can again see they're not quite as dense because they're falling less fast. So they existed all, well, up to about 2 at least, the ones I've done. And this is just to show you what the velocities look like. So this is the particle velocities. You can see the particle velocities are very non-uniform. So if this were in 3D, they would make structures, but because I'm restricted to 1D, I can only see waves. And what you see is you get very high accelerations, and then the fluid velocity changes very, very little. So. And then just to give you some idea of what's important, I plot here the different pressures, right? The granular pressure due to kinetic energy. You can see it's below 0.5. They're all at the same scale as the pressure. This is the pseudo-turbulent kinetic energy. That appears in the flux and the Reynolds stresses. But the PF peak pressure, you can see, is, well, it's the same order as this one, but it's much larger. So we could completely neglect the kinetic pressure, but this one is very important. To keep the system hyperbolic. Okay, and I guess the last example, if you want to see the, okay. The last example is the particle curtain. So this is the shock wave. So this is one where it's very important when you do your solver that you conserve energy, momentum, etc. So you have to make sure everything works. There's a lot of physics here because you're doing all the collisions, you're doing all of the shock capturing, so everything goes in there. But it is 1D, so we can do a 1D solver for this. What we did then is initialize, instead of having monodispersed here, we have a log normal. And here, in this case, I took 4 representative sizes. So I'm going to, with quadrature, says, well, instead of doing the whole distribution function with, say, bends, you can use 4 representative sizes and solve four sets of equations for those sizes. Okay, so we're going to put a shock in. I think this is Mach 1.4 or 1.7, I forget, but what you didn't get is what I showed you at the beginning. You can see here, I start the shock when the shock hits the curtain. This is the reflected shock. This is the transmitted shock that goes through the curtain. You can see that the curtain is moving and that the size distribution moves over. So the smaller particles, the whole curtain moves, and the size distribution changes. The mean certainly changes. This is the mean size. So the bigger particles get left behind at the back side of the curtain, and the middle of it is mid-sized particles, and the small ones move out. Some other statistics. This is the pseudo-turbulence is where the curtain is, which you'd expect because it's created by the drag on the particles. The gas velocity in this case, it's well, this is just to show that there's a shock. It's a very large gas velocity, and then the granular temperature of the particles actually is quite complicated. Well, you actually have 3 granular temperatures, 1 for each side, or 4, 1 for each side. And you can see that at different locations, it turns out to be very large right behind the location of the curtain due to the fact that particles bounce off. They get thrown back into the loop region. This is at point 1. Let me go to and at point 6. Point 6 is interesting. A point 6 curtain is almost a wall, right? And there you can see that the wall of particles, and then the shock gets reflected back and almost nothing goes through. Because when the shock hits the wall, it compresses all the way and makes it very little transmission, close packed. The curtain actually gets thinner, and then it sends the shock in the back in the opposite direction. So, and then the distribution of sizes is different too because of the fact that the different physics. And then just to show you, this is now what I'm plotting here is these are different initial conditions for the curtain, so very dilute and 0.1. And so what I'm plotting here is the average size at location. So the curtain was originally here, where the curtain's really about here at this time. And you can see that the average size, which is in green, you can see that the big particles are behind and the small particles have been moved over. So we're able to capture the size segregation due to the fact that the drag is different and the physics. And then when you get to be denser, it actually tightens up, but you still get a separation. Okay, so to conclude, hopefully I've convinced you that these Eulerian models can be applied to a wide variety of polydisperse flows. So for me, the compressible was actually easier because in the compressible flow you have energy equations, and incompressible it's harder because you've got to write you got to let the sound speed sounds. You don't want the acoustic waves, so you've got to have a solver that does a Poisson solver injected. But the important point is that we're using the microscale, the multiscale models that we get from the microscale simulations to get expressions for fluxes and source terms. So the key point is you need physically based fluxes and physically based source terms, and then you're able to go to a wide range of length scales. In my opinion, at least, developing the mesoscale model is, from a physics point of view, is more intuitive than trying to do an averaging and then close the averages, because you already, it's of course more restricted because you have to postulate a model, right? But that's what you do for hard sphere collisions in the gas. But once you have that, then it's just a matter of doing the mathematics behind it. So you can put in different mesoscale models and see how they affect it, and the closures at the moment levels will no longer be an issue. Okay. And then these, I didn't talk about it all, but there's a lot of numerical methods for high-speed compressible flows that you need for hyperbolic systems. But most of this is available in the literature. Not so less, I guess, for multiphase flows, but the two HHLC for gas and the ASM that we used are both well-known methods, and just really getting them to work together. Anyone notice that I had no viscosity? So I didn't talk anything about viscosity. So that's because in high-speed flows, it doesn't matter. It doesn't change the hyperbolicity. It's still well-posed if you don't have viscosity. But if I really want to do sedimentation problems, I got to put in the granular viscosity. I think for gas particle flows, it's well understood. The Peckley numbers tend to be very, very large, so the viscosity doesn't really do anything. But if you're looking at, for example, sedimentation where you have riverbed shearing, you need a viscosity model. But these have been done by other groups. For example, the groups in Grenoble, other groups, and those will be fairly simple to add onto the model. They don't change the mathematical properties. So I'm leaving that for future work to look at. Okay, so I think that's it. Thanks for your attention, and happy to answer questions.
Thank you very much. Any questions?
Thank you for the seminar. Thank you very much. So this is maybe a naive question, I don't know. So you say that your mesoscale model has to be deeply rooted into first principles.
If you want to be predictive, yes.
Yes. So about your slip pressure term, is it derived from like hydrodynamic lubrication theory, or?
No, it's Dwayne Zhang at Los Alamos derived from a term. We can show that there has to be such a term from kinetic theory.
Okay.
Because once you have a slip, in general, if you add a source term, you have to change it. There's a flux that goes with it in kinetic theory. So he postulated that it's an interaction, and then he derived this tensor that I use for potential flow. Okay. So for potential flow, you can write the exact expression to the interaction. Then the work that was done with Balachandra's group, they did a DNS, fully resolved DNS, and they had a method to extract it.
Okay.
It's very expensive and it's very noisy. So if at this point we need either a better method to extract it from DNS, but it's definitely there. It's pressure fluctuation. You see all the pressure fluctuations in the continuous phase, and you can't just ignore them. Right? They have to be modeled. But the model was strictly done for potential flow.
Okay, but could it make sense to for this term to arise from a lubrication effect, or?
Most likely, yeah. So
okay.
yeah.
Okay, thank you.
Thank you for the presentation. It was really nice. You were saying that now you're working with the spray combustion at the very beginning.
Yeah, that's actually what we started on, yeah.
Okay, because it seems quite challenging. You have evaporation and all the chemistry. Could you comment on that?
Yeah, I mean, most of those things are known, right? So the evaporation, there's been a lot of work on that. It's when you go, and you can do Lagrangian particle tracking, that works very well. With sprays, that maybe is enough because sprays disappear and then you don't have to worry about them anymore. Whereas real particles, of course, stay on forever. So the challenge with sprays is closing the moment transport equations. So you can't just add a kinetic energy equation. For example, you need to have higher order moments because there's not a lot of interactions. There's not a lot of collisions. So they go out and then the particles can have different velocities. It's closer to a radiation problem where you have to keep track of all the different speeds. So it's a closure issue on where you can stop closing. In this case, I stayed in the denser regime where particle-particle interactions are strong enough that you can do a closure that makes sense. But if, for example, if I had just particles dropping in a vacuum, that would actually be easy too because they'd all have the same velocity accelerate because they wouldn't see each other. But if you inject them at different speeds, you'd have to keep track of all the different speeds. And when you write an Eulerian model for that, you've got to go to higher and higher moments They capture all the different speeds.
And how would you manage the change in diameter?
That's actually not too. I didn't show it here, but you have an extra term in the polydisperse model. I left them off because they don't affect transport directly in terms of. So here I just put in a collision, and I put in. But collision could be change in diameter, so the C variable could be the mass, and you can have an evaporation term. So there would be a gradient with respect to C, and then there'd be evaporation rate. Same thing for heat transfer, the temperature of the droplets, you'd have the same thing. So you'd have additional terms here that, in my opinion, if you can do it in Lagrangian, you can do it in Eulerian. So whatever you do in a Lagrangian, it just adds additional term. So think of these as this is like the characteristic, the rate of change of velocity is this. And so this is the rate of, it's a pressure term that's hard because it's a collision term. But anything that you can put into a Lagrangian method, you can add. Then it's a question of closure, but that's a different issue. Yeah.
Thanks.
Maybe a general question is that you mentioned most of the applications you mentioned were industrial applications, but there's another field which is interesting, is more geophysical scale flows, typically, for example, explosions of, volcanic explosions, eruptions. Can you comment on this?
I think all the same models will work, So I don't think and people are using the same types of models for those, But the same approach works well. So basically, the volcanic explosions with particulates, the kinetic theory. This is high speed, so now you can do compressible, so you can sound nice. So so I don't see any reason why you couldn't use the same models.
Okay.
The scale of the computation will be huge.
Sure.
So you probably need, because these are, if you think of the models in terms of moments, these are Navier-Stokes equations, right? These are Euler's equations, but it's extended. So you need a really fine grid. Even the settling problem, I had to take a 1 millimeter grid to capture the kinematic waves. So if you then do averaging of this and try to do Reynolds average or LES, then you have more closures to deal with. So at this point, I've only worked at well-posed equations that are, if you can resolve everything, you get the physics. And then there's a whole other layer. How do you get a turbulence model when you don't resolve the scales?
You mentioned also dense flows and dense granular flows, for example, and the importance of viscous effects in this case. So, of course, in this case, we know, for example, that the let's say empirical relationship have a strong there's a strong relation between the pressure and the dissipation. So usually you have equations which link both. And so you said that that would not modify the hyperbolicity. That seems to be
you would have maybe if you look at
more
it,
complicated.
You would have additional terms. These are for the gas phase. So if you look at the pressure. For example, you're going to have additional terms for like the velocity, for example. I just put in drag here, but I didn't put in the dense pressure. But there's going to be a very tight coupling between the momentum of the particles and the friction. So you can write it like this, of course, but then it's very stiff.
Sure.
You're going to have a very, very strong coupling. It'll either be a frictional term on the right-hand side or something else. But I think adding viscosity is not difficult. Because you just put an additional gradient term here, but how you model the viscosity is difficult.
Sure.
I think one advantage of this is that you do have a particle pressure, so you can get regions where it's expanding, where there's no touching of particles, and when it's very dense, and where they're basically driven by the frictional pressure.
Okay. Okay. Thank you. Well, I think we will stop here. Oh, maybe Stéphane. Last question.
Last question. Thank you very much for mentioning hyperbolicity and well-posedness. It's a really interesting topic. We already, I think, discussed this at lunch 10 years ago, or maybe 5 years ago. I don't know.
Longer,
and my feeling is that, unfortunately, in the community of multiphase flow, and especially maybe among maybe more industry-oriented people, this topic is not present to their minds, and they sort of tend to neglect it or not be aware of it, and so on. Do you agree with me?
Yeah, no, exactly. Typically, and this is in Daniel's paper, they don't add this term, they add a turbulence diffusion term, which makes it hyperbolic, but for me it has no physics because there's no turbulence averaging. And so what I wanted to show when I started working on this is that there is a term that people that work on sedimentations, they know the particle fluid stress. And so if you extend that when you have velocity differences, just one small thing would make the whole system hyperbolic, and you don't need to worry about it anymore. So you don't have to add additional stuff. But no one else keeps track of that for an industrial system. It turns out, I mean, when you do a real system, the term is really small in most applications. It's what you need. When you look at for example, the sedimentation problem I showed you where you get these very large fluctuations, I could show you the eigenvalues. I plot the eigenvalues, and you'll see that the two eigenvalues that could potentially become complex, they're almost right next to the mean. So in terms of the physics, you don't see anything. But in terms of the math, it fixes the problem. So a lot of issues. The case where I saw the most difference was when very high-speed flows, where you get a shock coming at 1,000 meters per second, and then the velocity difference is really large, and then this becomes large. Basically, the particles then just blow up like this instead of all moving this way because of the large pressure that it creates. So, but for the low-speed flows, you have to have it to make it work, but it typically doesn't make a large difference except for the kinematic waves. That's why I wanted to emphasize that, because there are things that show up that make a difference.
Okay, thank you.
Okay, well, thank you again.